Hey guys, welcome to Unit 10, Section 7. Today we're talking about applications of volume and surface area, and then we're also going to be talking about scale factor. So the first question states, in order to model a home, you need to create 4 miniature pillars out of plaster. The pillars will be regular hexagonal prisms as shown. So the hexagon part is something we got to take into consideration. And then we have a diagram of what these prisms will look like off to the left. We know that they have a 12-inch height, and then each side of the hexagon is going to be 2 inches. So we need to think about our formula for a prism, and this is going to be the volume formula, because we need to think about how do we find the volume of the whole thing, because we're going to make the whole thing out of plaster. But the first question says, what is the area of the base of the pillar? So we need to think about this, and it might help if you just draw a hexagon off to the side here. So each of these is 2. And then we want to find the area. So we need to use the apothem formula. So that's 1/2 lowercase a times the perimeter. Perimeter is pretty easy to find. It's just going to be 2 times 6, which is 12. The apothem, we got to do a little bit of work. So we have to think about the center going down to the middle of one of our sides. And then what is this angle right here? Well, if you recall, we've done quite a few hexagons. That's going to end up being 60 degrees. So for this problem, we know that the bottom side would be 1/2 of 2, which is 1. And then the side opposite would be our lowercase a. That's the apothem. We just need to find the tangent of 60 degrees, because it's opposite over adjacent, and that would equal a over 1. And we could multiply both sides by 1, but that's not going to change the value. So let's just find out what the tangent of 60 is. And we get 1.73. We'll round that to. So a is approximately 1.3. Now, if we use our formula, the base area formula for this pentagon, it's going to be 1/2 times apothem. Oop. I messed up on the apothem here. Hold on. 1.73. 1.73, and then multiply that by the perimeter, which is 12. So we can just use our answer that we had up here. 1 divided by 2, and then we're going to multiply that by 12. And we get about 10.39. Now let's think about what we've done so far. That is the area of the base. So that's going to be 10.39, and we're in inches squared. So there's our answer for the first part. For part B, how much plaster is needed for each pillar? So this is where I was saying we need to think about the whole pillar. So from top to bottom, how much material is needed. So that's actually going to fill in everything about it. So that's going to be the volume for this one. Now the volume formula, if you recall, is going to be, since it's a cylinder, or a prism, it is base area times height. And we just calculated the base area in the previous problem. So we're just going to take 10.39. We're going to multiply that by 12. Okay, and if you type this in your calculator, you're going to get 124.68, and that would be inches cubed, because that's volume. Then part C says how much plaster is needed for all 4 pillars. So that's just one pillar we calculated. So all we got to do is take that number times 4. So 124.68, multiply that by 4, and we get 498.72 inches cubed of plaster. All right, and we're done with that one. On to the next one. Now this problem should look familiar. We actually have done a couple problems like these in the homework. The block made at the left is the shape of a shell of a rectangular prism. So we want to find the volume of the solid. Now we're thinking about, notice there's like empty space inside of the whole box. So the rectangular prism has some space that isn't included. So what we want to do, since we're talking about volume, so volume, just really quick, our formula is base area times height. In this case, we just have to calculate it for two separate rectangular prisms. So let's start with the larger one first. We'll put large prism just so that we know which one we're talking about here. So that one is going to be the larger dimensions, which is going to be 4, 5, and 6. So that's the outside of the box, the biggest rectangular prism. So all we have to do for that one, base area would be 4 times 5, and 4 times 5 is 20. So this is going to be 20 times 6. Or you could just do 4 times 5 times 6. That's the nice part about volume for this one. And you would get 120 millimeters cubed. The next thing we're going to look at is the smaller prism. So I'm going to put smaller. That one would be these dimensions. So we're not using 4 and 5. We're using the inner dimensions, which are 4 and 3. So 4 times 3 would be 12, and then 12 times 6. The height is still the same. We would end up getting 72 millimeters cubed. Now, 72 millimeters cubed is the space that is not being taken up. That's the empty space. So we need to think about the shell itself would be the difference between these numbers. So we're going to take 120 minus 72, and that gives us 48 millimeters cubed. Okay, so basically whenever you have a problem like this, you're finding the portion if it were one figure, so using the largest dimensions to find it if it were one figure, and then subtracting the smaller figure's dimensions. One more of these application problems, then we'll move on to scale factor. To complete a construction job, a contractor needs 78 yards cubed of concrete mix. The contractor has a conical pile of concrete mix that measures 7 yards in diameter and 4 yards high. So this is the key word. Conical meaning cone-shaped. So the first question says, how many cubic yards of concrete mix are available to the contractor? So we need to calculate the area of that cone. So maybe we want to draw this off to the side here just to help us visualize. Cone's pretty easy to draw. 7 yards in diameter and 4 yards high. So here is the height, that would be 4 yards. And then all the way across, we got 7 yards for the diameter. Now, if you recall, the formula for this, for volume, because we're thinking about how much could it fill, that's going to be 1/3 base area times height. So 1/3, and then to calculate base area of a cone, it is going to be pi r squared. So pi times the radius squared. Now the radius is going to be half of 7, which is 3.5. So be careful on that part. And then the height is 4. So let's go ahead, let's type this in our calculator here, pull this up. And comes out to be 51.31. That's yards cubed. Part B says, does the contractor have enough concrete mix to finish the job? Well, their goal was to have 78 yards. So we are definitely short of that. So that is a no. And it says, if so, how much extra mix is there? So we can't answer that because we don't have any extra mix. If not, how much more does the contractor need? So here we can answer this though. So 78 was the desired goal. So we just subtract these. And that comes out to be 26.69 cubic yards or yards cubed. That's how much concrete mix we are short to meeting our goal. All right, so these problems here, just make sure you read the directions. Think about, is your goal to find surface area or to find volume? But the application problems are really no different than what we've already been doing. Now, scale factor is a little different. The theorem here, you have to recall, this relates to the theorem that we used for area. If two three-dimensional figures are similar with the lengths of corresponding sides in the ratio of A to B, then the ratio of their volumes is A cubed to B cubed. This should say then. And then when we were talking about area before in the 2D unit, it was a squared to b squared. So just think cubed when we're talking about volume. If the ratio of volume from one similar 3D figure to another is 27 to 125, find the ratio of the corresponding sides. So this is giving us the volume. So if we know that 27 and 125 are the volume ratio, and we want to find the ratio of the corresponding sides, or like the perimeter ratio, we have to work backwards. So we're actually going to take the cubed root. This is something we just have to be comfortable doing. And then to do this, I'll show you how to type it in your calculator. The cubed root, you have to hit this f of x button. So the f of x button is about right there. And then we hit this here. It looks like the square root, but it has a space there where we can type in the little 3. So we're going to do 3 and then just type in 27. That comes out to 3. So the ratio is 3 to, and then let's just delete that and type 125. 3 to 5. So that's the ratio of the sides. The next one says, if the ratio of corresponding sides from one similar 3D figure to another is 10 to 15, find the ratio of the volumes. So this time it's giving us the side ratio. So we have to simplify this first. Hopefully that jumps out to you that that is not simplified enough. So 10 and 15 both have 5 in common. So that would become 2 to 3. And maybe it would help if we wrote it as a fraction rather than the ratio like that. It doesn't matter though. So 2 to 3, now that's the sides, so we need to cube it. This time we do want to cube the ratios to get the actual numbers. And I can show you how to type this out as well. So when you're cubing, hit 2, and then if you hover over right next to the square, there's this exponent with just a blank square. Then type in 3. That's how you can get that part. We would get 8 over, and then let's type in 3 cubed. And that comes out to 27. So this is the ratio of the volumes. Okay.